Hey everybody! So in this video we're going to look at a specific type of interference called double slit interference. And this is a PowerPoint presentation that I'm going to go through. I would just remind you guys, if you go to our course page, you'll be able to find this down here. Okay, right there. Double slit interference, the PowerPoint slides. But before we get to that, let me just describe what's going to happen in this double slit pattern. We're going to take two narrow slits, so I'll just represent those like this. So these are two openings, like so, and then another one right here. Now typically these slits will be sub-millimeter wide, so maybe half a millimeter or 1/4 of a millimeter wide. We're not so much interested in the width right now of the openings, because we're going to be concentrating on what's called the interference pattern. So what's going to be critical there is the separation of the centers of the slits. That separation distance we're going to call D in the formulas that we'll develop. Okay, so the idea is that this is opaque. So this part right here, light can't get through, and in between it can't get through. Oh, and by the way, typical Ds again are going to be maybe half a millimeter, a millimeter, something on that order. Okay, so light can get through the openings of the slits. And the question is, if we come in with one wavelength of light, because we want to see a nice pattern, so we're going to use one wavelength. So something like a laser. When they used to produce these patterns before we had lasers, they would actually use a prism to break light into different colors, and then a block, a small opening, just to let a very narrow range of color through. But in any case, so if I come in with a laser beam like this, so the laser beam is actually overfilling the slits. Okay, can you imagine that? What happens as the light goes through the slits? So if I did like a different view of this, a so-called side view, that would look something like this. So I would have opaque, then I'd have an opening of the slit, and then opaque, and then another slit. Okay, so I'm sort of looking down on top of this. So my distance D, that separation distance between the centers of the slits, would be like that. And then my laser beam I would represent like this. So the laser light's coming like this. Okay, it's definitely catching both slits, so it's all filled in here. Okay, so the question is, if I look downstream, let's say I put a screen downstream somewhere over here, what kind of pattern do I see on the screen? Now your first guess might be you just see two blobs of red light, right, where the light gets through the openings. But in fact, that's not what you see. And what this demonstrates is the wave-like nature of light and the fact that light can interfere. Okay, so what do you see? I'll sketch it, then I'll show you a photo, and if I see you in person, we'll produce this in person. But I'm going to draw a reference axis. So if I go right in between the two slit openings and draw an axis like that, that's a good reference axis, because that point right here on the screen is exactly midway of the two openings. Okay, so if you look at the light, what happens is you will see a bunch of what we call interference, sometimes we call them fringes, but they're intensity maximums, intensity minimums where there's no light, and then intensities in between. Now, right here, this point will always be an intensity maximum. Then there'll be a little bit up here, there'll be an intensity minimum, then another intensity maximum, then an intensity minimum. But the light actually looks spread out, because even though that point right there, right in the middle, is an intensity maximum, you're going to see some light as the intensity drops off. Okay, so it'll fade. Then there'll be sort of a dark fringe or a spot, the center of that dark fringe will be a true intensity 0 point. Then there'll be another bright fringe of spread out light, then a dark fringe, then a bright fringe. Okay, it'll be like that. And then it'll be symmetric, the same thing over here. Okay, so now what I can do for reference is I can refer to a spot on this screen one of two ways. So one way I could do it is I could draw a line right from that intersection point, let's say to right there. That would be an intensity maximum. So I could give this angle. Okay. The other way we could do it is we could actually put an axis right on the screen, and we usually call this the y-axis. So y equals 0 would be right here, right at that intersection point right there with this reference axis. That's always going to be an intensity maximum. And then I could give the y value positive or negative to specify a point. Okay? But what we're going to be interested in is these points where we're getting intensity maxima, right in the centers of these bright fringes, and then also where we're getting no light, right at the centers of these dark fringes. Okay, that's what our primary focus will be. But let me go ahead and show you, if I start the PowerPoint presentation, that is what a pattern would look like. Okay, now you can see that we don't have uniform brightness. In fact, we get the brightest intensity right at that center fringe. This point right here, this would be exactly at the intersection of that reference axis in the screen. So if I trace that back to the double slit, that would be right in between the two slit openings. Okay, so that the center of that would be an intensity maximum. You can sort of see this dark fringe. The center of that would be an intensity minimum of 0. Here's another bright fringe, so the center of that would be an intensity maximum, relative maximum, then a dark fringe, bright fringe. Now the fact that the intensity is dropping off generally as you go away from the center of the pattern, that's a result of what we call diffraction of light. That's a result of how light actually spreads out when it goes through a slit. We're not going to be focusing on the diffraction of the light, the fact that the intensity drops off as you get away from the center in this analysis. We're just going to focus on the interference where we get relative intensity maxima and minima, these positions of the centers of these fringes in this video, when we look at the interference. Okay? All right. So if we go to a drawing here, this again represents a side view. So I'm going to call the separation of the two slit openings D, little d, and you'll see later we're going to use this distance between the openings, the slits, and the viewing screen. We're going to call that L. Now, typically when we do this, right, this L is much, much bigger than this D. This is not drawn to scale. Again, this D is going to be on the order of millimeters. The viewing screens are usually going to be on the order of meters. So this is not drawn to scale, but I need to fit it on the slide. All right, so these rays represent the laser beam coming in, right? And I'm interested in this point P. So this point P on the screen up here, what is the condition that we need so that that is an intensity maximum or an intensity minimum? Okay, or if it's neither of those, then it's going to be somewhere in between, right, intensity. So if we focus on that point P, what we can do is this. We do this construction, and Young gets credit for doing this first. So sometimes the pattern that we were looking at is called Young's double slit pattern. So I can again reference that point P with an angle theta. Then what Young said is, okay, look, it's because the light's going to spread out when it goes through these two slits, and again, that's the nature of waves that we call diffraction. What Young says is, let's treat this as we have two sources of light. In fact, 2 point sources of light where the light just spreads out uniformly. Now that is an approximation because if we actually look at the diffraction, it doesn't spread out uniformly. But we're going to assume that it does. That's why we can't address in this analysis the fact that the light intensity drops off as you get away from the center of the pattern. We're only going to be looking at where the maxima and minima are in the interference. Okay, not the actual size of the maxima, intensity maxima. So we're going to assume that the light spreads out uniformly from this point source right here, we'll call that source 1, and this point source here, source 2. So let's again focus on this point P. For source 1, the light would have to travel a distance of R1 to get to point P. For source 2, it has to travel a distance of R2. So what Young said is, oh, we treat this as a two-wave interference problem. So what I'm interested in is the path difference between R2 and R1. Okay, if you recall in the other first video, that path difference between the two waves introduces a phase difference. Okay, so, and I'll echo that again a little bit later. Okay, so here's what we do. We drop a line like this. What we want to really make is an isosceles triangle. So the two sides of the isosceles triangle are R1 and R2. Okay, this angle right here is going to be very close to 90 degrees. Very, very, very close to 90 degrees. Okay, so what we're interested in is this bit right here, this path difference. That's what we're interested in. Oh, in fact, I'm sorry. When I said very close to 90 degrees, in fact, that is going to be a 90-degree angle because this is I get two right triangles right here that make up my isosceles triangle. Okay, yeah, so that's a 90-degree angle. Okay, so I'm interested in this path difference right here. Okay, so how do I figure that out? All right, so we're going to make an approximation here, but it's a really good approximation. Okay, first of all, if this is angle theta right here, this angle, I claim that this is angle theta right here. And to see that little blue triangle right there? I blew it up over here, right? This angle right here, right? That's angle theta. You can see that in my drawing right over here. This is a right angle. So this right here has to be 90 minus theta, okay? Oh, because I have a right triangle right here. This blue triangle is a right triangle, right? This angle, again, is 90 degrees. That's this angle right here on the other side. So that means if I look at this right triangle, this, and this, that's got to be angle theta. Okay? So that's how we get that that's angle theta. Then I'm going to look at another triangle. But here's where my approximation comes in. This is an isosceles triangle, right, with sides of R1. Now, I claim that the two angles here, these two equal angles of my isosceles triangle, are very close to 90 degrees. The reason that's true is that L is going to be a lot bigger than D. A lot bigger than D. Okay? So I'm going to make the approximation that these two angles are 90 degrees. I know that can't be true if this is a triangle, but I'm assuming that this angle up here at the tippy top of my isosceles triangle is really, really, really small. So I get approximately 90 degrees. So I'm going to make a this yellow-green triangle, right, you see it, where this angle now, I'm assuming is 90 degrees because I assumed that this angle was 90 degrees. Okay, so here's that triangle over here. So look, this hypotenuse, this is the hypotenuse of that yellow triangle. That is the separation of my slits, D. But I know this angle here is theta. I'm interested in this green bit. That's the path difference. So using this yellow right triangle, I can say that that's got to be D sine theta. And that's how I get that my path difference is D sine theta. Again, it's this weird approximation that I'm assuming my isosceles triangle has two angles of 90 degrees down here. They're almost 90 degrees. And it's a really good approximation because we're using the sine function. Okay, it turns out. All right, so my path difference is D sine theta. So then what Young says is, I go back to my two-wave interference. And you might recall that if the path difference is an integer times the wavelength, that's going to make the waves in phase when they arrive at point P, assuming that they leave in phase from their respective starting points. But Young says, well, yeah, they do, Because remember, this is one beam of light that's hitting these slits. So the waves that leave these two sources are in phase when they start because they're coming from the same beam. So d sine theta equals m lambda. That should be the condition where point P is an intensity maximum. Similarly, if the path difference is an integer plus 1/2 wavelength, then recall with two-wave interference, if the waves start in phase, when they get to that common point, they should be completely out of phase. If that path difference is an integer plus 1/2 times the wavelength, they should be pi out of phase. So Young says the condition for point P to be an intensity minimum, which is 0 intensity, should be m plus 1/2 times lambda, right? Where m here is just an integer, 0 plus or minus 1 plus or minus 2. We're going to write it like that. So here's the condition then for our interference pattern. This predicts where the relative maxima are and where the intensity minima are, the intensities of 0. Okay? Pretty cool. Well, it turns out that this works, actually. It describes things that you see on the screen perfectly, particularly when L is much, much bigger than D, which is usually the case. Okay, now we can put this in terms of actual position on the screen using the y-axis, the screen axis. Okay, so what you can do is, if I imagine there's a y-axis on this screen, y equals 0 will be straight from the center of the slits, right along this reference axis. So point P would be at some positive value of y. Well, look, I can draw this blue triangle, and again, this is not to scale at all. Y is going to be on the order of millimeters. L is going to be on the order of meters. Okay? Well, I mean, y could be a little bit bigger than that, because it just depends on how much the pattern you can actually see. But y is going to be on the order of millimeters, centimeters, typically. Okay? But in any case, look, this angle is going to be relatively small. That's the point we want to approximate. Because L, again, is going to be on the order of meters, y is on the order of millimeters, centimeters. So we can use a small angle approximation. Now, without any approximation, it's true that the tangent of theta is y over L, right? Opposite over adjacent. But because the angle theta is going to be small for these maxima and minima of intensity, we can say the tangent of theta is approximately the sine of theta. So the sine of theta, we can say, is y over L. That is an approximation. But then what you can do is, in this d sine theta, right, equation, you can replace sine theta with y over L. So that gives you actual positions on the screen, right, using the screen axis. So I'm just rewriting the maximum and minimum conditions as y equals m lambda L over d. That's where the maxima will be. And y equals m plus 1/2 lambda L over d for the minimum. Or the minima, I should say. Okay? And if you notice, right, look, m equals 0. Right, that the only way you can satisfy that is with theta equaling 0 or y equaling 0. Okay? So if m equals 0, you're going to have a maximum, right? Because you get m lambda or m lambda L over d, and that corresponds to y equals 0 or theta equals 0. So that's describing the fact that you always have an intensity maximum right here, right across from the center of the slit separation. Okay? All right. So here are the equations for the Young's double slit. This is the equation in terms of angle theta. This is the approximation in terms of screen position y, and it predicts the pattern really well. Okay? So if we go back again to our picture, I should do the spacing. Yeah, I'm sorry, I forgot. You can now look at the spacing between consecutive maxima or minima. All right, so what is the separation, the length separation of the centers of the bright fringes, right? Or the centers of the dark fringes? Well, all you have to do is, since we have this in terms of y, just take two consecutive maxima. So for instance, m equals 0 and m equals 1. Right? So if I take y equals 0 and y equals 1 lambda L over d subtract, I'm going to get lambda L over D. But you can do that for any consecutive maxima. If I take m equals 4, m equals 5, I subtract the y's, I'm going to get the same delta y of lambda L over D. Same thing with the minima. Take two consecutive minima, m equals 1 and m equals 2. Subtract those two minima y's, you're going to get lambda L over D. Okay, so what that says is that the maxima centers and the minima, right, the centers of the bright fringes, the maxima points, are separated by lambda L over D if you look at consecutive maxima. Same spacing for the minima, consecutive minima. So again, if I go back to my pattern, let me end this show and just go back to the pattern. See that pattern right there? So this right here, right at the center, that would be the m equals 0 maxima. Okay? The next maxima would be over here for m equal 1. Right? That would be positive y, so we'll go to the right. The separation of the center of this bright fringe and the center of this bright fringe is lambda L over D. Now that's the same separation as the center of this fringe and the center of this fringe, the consecutive maxima. And I can go in the negative direction if I want to also and find the same spacing. If I look at the centers of the dark fringes, so that point is the center of the first dark fringe, and here's the center of the next dark fringe. That spacing between those centers of the dark fringes, the minima, is also lambda L over D. Okay, so it's equally spaced. So Young explains where the centers of these bright fringes are, where the centers of the dark fringes are, the fact that you're getting bright fringes and dark fringes. Again, though, Young's analysis doesn't explain why the intensity is dropping off as you go to the right and to the left of the center. That is because of the way the light spreads out. He assumes it spreads out uniformly, but it actually doesn't. We'll look at that spreading out, the diffraction, when we get to the diffraction part of part 2. But now we're just concentrating on where the centers of these fringes are. Okay? All right. Oh, I do want you to notice that if I change the wavelength of the light, if I go down in wavelength, the spacing of the centers gets smaller. So the pattern, right, will shrink, if you will. The centers of the bright fringes will get closer together. The centers of the dark fringes will be closer together. Similarly, if I keep the wavelength the same, but I make D bigger, if I increase the separation of the slits, the pattern will shrink. The centers of the bright and dark fringes will get closer together if D goes up because delta Y goes down. Okay? And again, if I see you in person, we'll look at that. I'll show you that. Okay, I'm going to end right now. Bye. I think that's all. Oh, I did want to say, let me show you in the summary notes that the stuff that we just went over is summarized right here, right, in the summary notes for part 2, Young's double slit. There it is right there, this top part. Okay. Now I'm going to go